I'm gonna click on the field. So there's my field, and now it's waiting for me to define something, so I can click over here. And then I can enter a function, formula, or I can use a table. Okay? So in this, if on the board, this is what I have for my thickness. Basically for the first 1,000 millimeters along the X direction. So in other words, when I move from here to here, the first 1,000 millimeters in this direction, I'm gonna have a thickness, my blade's gonna have a thickness of 5, right? So from 1,000 to 3,000 millimeters, I want my thickness to vary linearly. So that when I get to this edge, along the edge, my elements are gonna have a thickness here of 8 millimeters, right? So it's basically gonna be like this. If I look along the side of my part, my thickness is gonna go like this, and then it's gonna expand out, right? That is what it's gonna look like. So I'm gonna come over here, I need to somehow tell NX that this is what I want my thickness to do. So I want my thickness to vary along the X direction in this way. So the easiest way to do it is just use a table. I only have to use 3 points. I have to use the starting thickness, this thickness right here where it changes. So it's gonna change from here to here, so I give it this thickness and this thickness. By default, in between those two regions, so in between 1,000 and 3,000, most programs are like this, it's gonna vary it linearly. So I only need to define 2 points. It'll create a straight line, and then it'll use what value to use based off of that straight line. Yeah.
So if you have 1 point in the middle, where you try to, like, instead of having 3 points on the linearly varying part, we try to do exponential. If you
I can tell it to use exponential.
Okay.
By default, it's gonna use, I have to do 2 points. To create a line, I have to use 2
Right.
points, right? So basically, well, that's what I'm doing. I have a flat horizontal line, so I give it 2 points. And then I have my line at an angle, so I give it 2 points. And it'll interpolate between the two. It'll linearly interpolate to get the other values that we need. So basically, even though I'm doing this and we're gonna look at it, it's nice and vary the way we want linearly, it's only the thickness at a point, right? Because when we solve these equations, we're only solving the exact thickness at point. We only give it the nodal value. It's the thickness of that node, which really be defined in our model. Alright, so I'm gonna come over here, I'm gonna do the table. So it's gonna come up and it's a thickness field, okay? So we can't just randomly create it. We can randomly create a field, but can we use that field for thickness? The answer is no. So the answer is gonna be no, that we can't use that field for thickness. We actually have to go through this process. And there's a way to find the thickness field and do it a different way, but this is normally the one that makes sense. Now I want my thickness to vary along the X direction. That's basically what it's doing right here, right? So X, there's my thickness. So thickness is gonna vary along the X direction, correct?
Yep.
Alright, so I want to do that, so I'm gonna come over here. So my independent variable I want it to be X, right? So I'm gonna come over here. Now normally, a lot of times we'll come in, we can do Cartesian, we can do cylindrical, we can do spherical. We can select any one of these, but since I only have my thickness changing along one direction, I'm gonna come in here and I'm gonna pick weight. Now watch what it does. It automatically defined X over here. Did you see that? X is my independent variable. So that means whatever I'm given in terms of an equation, I'm gonna orient my axis so that the X direction that I pick in my model, that's the direction that it's gonna change it, okay? So right now, my X is actually pointing up, right? So I'm gonna have the opportunity to make X change the way I want. X point in the direction that I want, okay? Now that's the next step. So I did the length, that's important. I'm gonna come over here to the spatial map. So this is where I'm gonna do it. So, like I said, if I went and I drew it, when I picked the plane that I wanted to do it in, if I picked it very carefully, I could have made it correspond to my picture here. In which case, I would just leave this global, okay? But I don't want to do that. I want to define a Cartesian coordinate. This is the best way to do it. So you always remember know how to do this. If you learn how to do this, you can do anything, right? If If you're on global, then if you have something weird going on, then you're stuck. Okay? So we're gonna do our Cartesian. So now it's waiting for me to pick a coordinate system. I can go in and try to define a coordinate system, but it wants to create one, okay? The thickness is very picky. Most other things we can create a coordinate system and then pick our coordinate system. Like we did for the beam, remember when we had the beam sliding along that angle, we went and defined our coordinate system and then we defined our boundary conditions based off of that coordinate system. So here with the thickness, it really wants to create the coordinate system in this step. It doesn't want us to go define one and then try to pick it. Okay? If I'm just defining some general function, then it's easier to do that. So it wants to create it, so I'm gonna come over here, I'm gonna click on this. I want to go ahead and create the origin, and it's easy to do x-axis, y-axis, right? Alright, so if we look at the picture on the screen, I'm gonna put it in that corner of my plate, right? So I want where you see the x of c and z of c on the NX. That's the little corner I want to put it in, right? Alright, so I'm going to come over here. I'm going to go ahead and zoom in. I'm going to come over here and pick intersection so there's no, so I know exactly what I'm picking. I'm going to come over here. I'm going to tell the intersection of those 2 points. So that little dot right there, the little gold dot that it put there, that's the origin. So now I'm going to go ahead and specify my x-axis. I want it to be in this direction. Why are you picking it up? Never get anything. Alright, so I'm going to go ahead and pick this edge. There it is, and the x-axis pointing in the direction that I want, right? If it was pointing in the wrong direction, I just need to click on that and then flip it. Alright, so I've got my x-axis the way I want, so I'm going to come over here, I'm going to pick my y-axis. And there it is, that's how I want it. I hit OK. Boom, it has my coordinate system right here. And now you see this popped up right here. So now it's waiting for me to enter this table value. So it sort of started the table. The only thing you have to remember is 3 things. The row ID it's going to do for me automatically. I need to tell it the x value and the length that I want. So the length is going to be my thickness, right? The length will be my thickness. So I'm going to click down here in this little area right here. At my coordinate location, x equals 0, what do I want my thickness to be? 4. So I'm going to go 0, comma 4. 4? 5. So I do 0, comma 5. I can click on the check mark or I can hit enter. And notice that it threw it up here in the table. Then the next one I want to define is what? 1.5. So 1 and 5? No.
What do you want to define?
1,000.
1,000.
Yeah.
So 1,000, comma 5. And then the last point I want to define is 3,000, comma 8. Alright, so I defined the 3 points to create that. This right here tells me that it's going to interpolate linearly, okay? This is the default. This is what most do. I can actually go here to here, and here, you don't want to do that. So here I can do different things. Alright, so I hit OK. There it is, it created it, it's green, it's checked, I'm done. Now, the question is, did I do it right? This is where we check. I right click on this, and you see this? This is there by default. It's something we do a lot. Okay? So it's in there by default. I'm going to come over here, plot thickness contour. It's going to plot it, and I can look over here. I can look at my scale. I'm like, yeah, that looks okay. I can come over here, and I can edit my display. And now I'm going to come over here and use cubes. And now when I hit OK, that's basically what my cross section is going to look like. what I want, right? So this tells me my thickness is correct. Alright. So I have my thickness in, I want it exactly to be like that, so I'm done with that. Now I can come over here and I have to return to my model. So I'm now back into my model, I have my mesh done, I have my thickness done, I'm ready to go into SIM and define my boundary condition. So I'm now in SIM, I don't want my mesh on, it just clouds up stuff. So now when we do 2D and 3D, we don't need our mesh, we're usually not taking nodes and defining boundary conditions or on nodes, right? We're defining it on our geometry, so there's no reason to have the mesh turn on. Alright, so now I'm gonna, if I look over here, what does this tell me? Fixing all degrees of freedom along edges 0, y, and x4, right? So along these edges I want it fixed constraint, all degrees of freedom. That makes it easy. I come over here and click. I want to do fixed constraint. And I select those edges. It said no, so I need to come over here and do my edge. Boom, boom. Okay, there it is. It does the stupid offset thing. Now I'm going to come over here and change that. Edit display. And now it's usually what we want to see, right? It's just a symbol, but it's actually on the boundary, so it makes sense. It's not just top, this line that's displayed offset.
Isn't it along the other edge? 0, 1? Oh no, x4. Yeah. Because it's off of your non-global coordinate system, right?
I'm using my local, it doesn't matter, I'm using my local coordinates, the one I define. When I define the thickness, I put my coordinate system over here, my x and y, right?
Oh yeah, you're right.
So I'm following this, I mean, this is why you will try to make the two correspond, because it's easy to get lost.
Yeah.
As long as I drew, yeah, so this is the long edge, right?
Yeah.
This is the 4 meters, this is the 3, so I'm fixing these two sides. So this is exactly like what's up on the screen. Alright, so now I'm ready to define my pressure. Okay? My pressure is going to be based off of this equation. Alright, so there's two ways. Notice when I created the thickness field, did you see this? When I created my thickness field, I put it right here. So that's why I said I could have went and created the field and then went and did the thickness and told it to use that field. Okay? But I did it all at the same time. I did it when I did the thickness and I created the field inside of that process. Okay? So there's many ways to do different things. So here, this field that you see right here, this is for the boundary conditions. This is for the SIM. These are the fields that I create in the SIM. This over here is fields that I create in the FEM. Alright, so I'm going to come over here. I can right click over here and I can tell spatial pressure formula. That's because I'm going to give it an equation. I could have done spatial distribution, pressure versus time, force versus time, spatial temperature formula. I could have come over here and done the same thing, but now with the table. Alright, so I could create it this way, or I can go in. Let's do it this way. Well, actually, let's do the other way, and then I'll come back and do this way. How's that? Alright, so I'm going to come over here. I'm going to create my pressure. I click here. I'm going to do pressure. I'm going to do on this surface. Blah, blah, blah. Okay, pressure right here. I'm going to go ahead and change the units to Pascal. I always do this. It doesn't really make any difference. It doesn't always do it upon. And I'm going to see this. This is where I did the units, right? This we've never clicked on before. I'm sure when you were doing stuff you clicked on it before. But we never haven't been before. So I click on this. I'm going to do new field. I can do existing field. Alright, so I can do new field. I can do table of fields. So I'm going to come over here. I'm going to do, it doesn't exist, right? So I'm going to come over new field. I'm going to do formula. I'm going to enter equation. It tells me it's pressure. I'm going to come over here. Now, our pressure equation that we see up here is a function of what? X and Y. So when I define my equation, I need to have those X and Y as independent variables. They're independent variables in this equation, right? So the way I tell NX that X and Y are independent variables is I'm gonna click right here, and I'm telling you, these are all the things we can change, okay? That's a lot of stuff. So I'm gonna come over here, all I need to do is tell it Cartesian. And notice that it says independent X, Y, Z, that is what I want, okay? Because basically I'm telling NX, I'm gonna create an equation that has X, Y, and Z as my independent variables. Alright, so I've got that, and then I'm gonna come over here, I'm gonna do spatial map. It's not showing me, I have to click on it. I'm gonna do spatial map, and this is where I tell it where X, what X, Y, and Z, where's the coordinate origin? Okay? It needs that. So I'm gonna come over here and I'm sliding this over here on purpose, okay? I'm sliding this across because these are the coordinate systems that I created. When I created thickness, these didn't exist. After I created the thickness, these were created. Okay? So I wanted to use the same coordinate system, right? That I went through and I defined. So we'll do that in here. So I'm gonna go spatial map, I'm gonna click here, I'm gonna do Cartesian. So now I need to specify, and I'm just gonna cruise across here and I'm gonna click on it. Okay? And boom, it picked it for me. Okay? And notice that it changed, see how it defined them right here, X and Y right here? It put that in there as soon as I clicked there. So I put them in there, so now it has pressure, it has the units right here. Again, I'm just doing this for the heck of it because it really doesn't do anything. I'm gonna click here on this, and I can come on and tell it Pascal. Alright, so now it's waiting for me to create my equation. So that's what this line is for. So it's similar to the line when we got the table, right? We gave it the X and Y, now it's waiting for the equation. So I just have to type in the equation. So I'm gonna come over here, this is the equation that you see up on the board. I'm gonna go 2 divided by 3, and then I'm gonna multiply this by times, and then I'm gonna go X, and then I'm gonna go times 4 minus Y, and then N squared, and my parentheses, and then N that, and then somehow everything's gonna be magically okay, right? Now, this is what I want my force to look like, right? Yes?
Yeah.
Looking at the equation, this corner over here is where I have 8 pascals, right? So in this corner over here, what are my coordinates? 0 for X, 3 for X, right? 3 for X and 0 for Y. So that means I'm gonna come over here, I'm gonna 3 in for X, 0 for Y. When I put that in, the 3's cancel out, right? Then I have 2 times 4, now do you understand where the 8 comes from? Okay? That's where the 8 comes from. Now when I'm working inside of NX, everything's in millimeters, right? So this 4 here in this equation is in what? Meters. So when I'm coming over here and I'm defining my equation here, 2 times 3 times X times 4 minus Y, that 4 there needs to be what? 4,000. Now, I'm going to click on the check mark. The check mark is very important because if I check on it and if nothing happens and everything's good, okay? If I see something change, something pop up, then not good. Okay? So we always, NX is one of those things you really have to pay attention because it tells you what's wrong. Okay? NX, a lot of the stuff, it tells us what's wrong. So I'm going to hit check. I'm going to check it out, see if it works okay. It comes back, what? Dimension mismatch. What happened?
Your 2/3, you're leaning to be 2,000, 3,000.
Yeah, it's just a constant.
Oops, 1,000.
Plug in the
pass down the fifty.
Nah, I'm just telling you, I'm just giving it an equation. That's not why it's giving me this error. You'll see. Technically, my equation should be unitless. So if my equation should be unitless, this just tells it it's gonna use the values it's gonna make in Pascal, okay? That's what that's telling me. Where's my problem? I have 4,000 minus millimeters. I must have millimeters minus millimeters. If it was 4,000 millimeters minus y millimeters, I'd be okay, right? So basically, I need to make y the same units as the 4,000. 4,000 is what? Unitless, right? So how do I make the y unitless?
1,000 Y.
Huh?
1,000 Y. Times Y.
How do I make y unitless? Divide by length, right? I divide by millimeters. I'm gonna come over here, I'm gonna take this y, and I'm gonna go divide it by 1 millimeter. If I just put mm, it's thinking I'm gonna use the variable mm. If I put 1 mm, then it's reinterpreting that as 1 millimeter. So I have millimeters divided by millimeters, right? So now I can do the 4,000 minus y. All right, now I said this should be all unitless, right? So what's the other problem I have?
Do the same for x.
The same thing for x. Okay? So I'm gonna come over here just to make sure. I'm gonna put this parenthesis there, divide by 1 millimeter, and times. Now, the reason I could use x and y is because they're independent variables. Okay, when I created this over here at Cartesian and it threw x, y, and z up here, it also threw them down here, okay? Yes.
Couldn't you also solve the dimension problem by just telling it that 4,000 was in millimeters?
Yeah, but my equation doesn't come out in units. I would still have to divide by millimeters squared. The units come here.
Okay.
So this equation, I basically want to do a unitless thing. I could make 4,000 millimeters minus that, but it's still gonna give me the same error. Notice how this okay lit up. So I did it, I'm okay. Okay. And that's what it did, right? I don't want it there, I want it going the other direction. It looks like I want it to look, right? How do I test it? I want it to go the other way. First of all, I want it to go the other way, so I'm gonna edit this. I'm gonna do this, edit.
Minus.
And now this is looking the way I want it, right? I'm making it look like this, right? So it's it's looking like that. The question is this right? So I can get a better display of this if I come over here and I can try without that. Edit display, I can go ahead and expand it, I hit OK, and now that's what it looks like, right? Is this the same as this? This really, I have to do it this way. Is it the same? Yeah. The only question is my force right? So just like we did the thickness, I can right click on this. I can come down here and plot contour. There's my contour. It's over here, I can put it. So here's my contour. Did I do it right? Yes? Everybody's in agreement? It's not right. Why is it not right?
It's in megapascals.
It's in megapascals.
Mm.
Is 7 pascals the same as 8 megapascals? I'm sorry, is 8 megapascals the same as 8 pascals?
Oh.
No. That's a huge difference, right? Where does the problem occur? Where's my problem?
Units you define.
No, I can change it. Remember I said I was just changing it for the hell of it? Wasn't gonna do anything anyways. I guess I could try to make this, I never tried to do it this way. No, I can't. Where's the problem? So if I look on the screen and I look at the board up here, on the screen on the board up here, I have meters times meters kind of thing, right? I have X meters multiplied by technically 4 meters, right? So when we did this, it was 2 meters, well the 2's over here, it was 3 meters times 4 meters, right? The problem is in NX, I have to define everything in millimeters, right? So I have millimeters, 1,000 millimeters for this. I actually end up having 3,000 millimeters times 4,000 millimeters, right? So I'm bumping up the magnitude by 1 times 10 to the 6th, 1,000 times 1,000, right? So I need to divide by what? Huh?
Million.
A million. Okay? I need to divide by 1 times 10 to the 6th. Okay? Because this equation on the script on the board, it's meters. Okay? I have meters times meters. When I wrote the equation in NX, I have to define it in millimeters. So I have 1,000 millimeters times 1,000 millimeters times. Okay? So I bumped up the amplitude. So I just need to come to my equation right here. Instead of dividing by 3, I just add 360. 3, 1, 2, 3. Okay. And I hit OK, and the world is good again. And now I can come over here and I can draw my contour. And now I can look at this. And what does this show over here? So it's 7.76 times 10 to the minus 6 megapascals, so that's really pascals, right?
Yeah.
That's in pascals. Now technically I should have come over here. I think I can change the units on this guy. Now it tells me it's in pascals, right? Now, all right, if it's supposed to be 8 pascals at the corner, why do you have 7.7? That's a really good question. No, you weren't gonna ask. Alright, Dave and I. Alright, so we're now gonna look why that is true. So it's defining pressure over the elements, right? The pressures over an area. So watch what happens when I tell it to give me the value. This little question mark here is where I click on it and I can pick anywhere in my model and it'll tell me the value, right? In this case, since I'm looking at pressure up here that says pressure, I'm gonna click on something, it's gonna give me the pressure. If it was displacement, it would give me displacement. So I'm gonna click on this, I'm gonna come over here and watch, it highlights the whole element. Here you can see it better. See how it's highlighting the whole element? So when I click here, I can't get the pressure at that little point. Because pressure is not defined over a point. It's defined over an area. So what it's giving me is the average pressure for that area. So I click here, it gives me the value, you can see 7.768. That is the average pressure over that element. If I make my element smaller and smaller and smaller and smaller, eventually I'll get closer and closer and closer to 8, right? But I will never get exactly 8. Alright. Now, this is all hunky-dory and everything. It's not, I'll go ahead and solve it. So we've defined everything. I can go ahead and save. Okay. Oops, not save, solve. I close this. Oh no. See if it lets me get away with it. Yeah.
It happens a lot. I think it's just an operating system thing.
Oh, does it happen on the? I never see it. So I'm running from my machine.
Yeah, that's what solves it.
I like my machine. Alright, so here it is. I can look at the displacement. This is displacement. I can come over here. Now we start looking at things banded. So I'm going to come over here. I'm going to do it. I'm going to do banded. And we've all learned a long time ago that displacement is very, very accurate, right? I can have a very coarse model and get really good displacement results. Okay? So that's my displacement. I really need to look at the stress. So I'm going to do stress element nodal. There it is, and that's what the stress looks like. I'm going to come over here. I think I should surface. It's kind of choppy. Actually, okay, there we go. I can see that color there. I was like, man, it's kind of great. Alright, so that's kind of what it looks like. Typically, that's not very good.
Why is at the very tip of the corner there less than like right around it?
Where?
Like where you have your highest stresses, the very corner elements are like it's orange, while it's around it it's red. Why is that less?
Why don't I have any stresses there?
Well, you do have stress, but why is it not red like the ones around it? Why is it not higher?
Right here?
No. Where you have your high stresses, yeah. Why is the very corner element? Why is that orange versus
Oh,
the
why
ones
is it
around
orange?
it are red? Yeah. You'd think that one would be red. At least I would think.
It is just averaging, but again, technically I should have infinite stress there. If we were solving the equation, if we solved this, only because you guys won't know this, only because it's like graduate level mathematics where you actually start looking at, you defining the correct equations for stress and strain as a function of x and y kind of thing. So if we were doing that, we would learn from the stress equations that the stress there is going to be infinite, and it's a problem with the equation. like when we have plastic stress. What's the stress when we have plastic deformation? You guys know that?
Could be whatever.
Now, if we have elastic deformation, that means it's gonna deform. We apply a force, it's gonna deform, right? We take the force out, what happens?
Bounces back.
It goes back. So we've all seen the stress strain diagrams, right? So we have stress, we have strain. I can do stress and displacement kind of thing, right? What does our stress strain curve look like when I have plastic deformation?
Increases because your area.
It's flat, right? Flat and how? Flat as in horizontal? Our strain keeps going up, but our stress, what? Let's look at displacement versus stress. I don't know how many different figures you look at when we do this is 450, right? This is where you should learn this in 450. So we did the stress concentration kind of thing, right? When we had the cylinder, when we did the hole in the plate, we like the stress is like 2.5 right there, we have stress concentration. We did the little equations and stuff. Normally, if we do stress strain, we kind of look at it, it goes up like this, right? And then we have some maximum stress, and then it kind of levels out. So it's like horizontal. So when, at that point, that's how we define where the elastic point is, right? That's how we define what we do, when we come up with our modulus of elasticity, it comes from that curve, right? It's a straight linear fit on that curve. Now, when it goes over that little hump and it levels out, that's when we have plastic deformation. When we have plastic deformation, it doesn't take any more stress to displace it. So it's like, once you get to that point, you keep you'll see a little drop. It's kind of like the concept of friction. If I apply my force, what's true about when I start sliding?
You need less force to keep it moving.
Even when you're trying to push something real hard and it starts moving, what happens? You almost slam into whatever it is you're sliding, you almost fall on your face. Because at the point when it starts sliding, it takes less force than it does to get it to slide, right? You have to exceed some force and then all of a sudden it starts sliding and the force drops, and that it takes less force to keep it sliding now. So this whole thing of plastic deformation is kind of the same thing. We apply this force, we apply this force, we apply this force, it's still gonna come back when we release the force, and then we get to the point where we have plastic deformation, it's all of a sudden, it takes less force to stretch it down. It's like saran wrap, right? You pull it, you let go, it goes back, but then all of a sudden, it's like at a point when it starts plastic deformation, it starts stretching, then it takes less force. So, equation-wise, you can't do that. So, when we're doing finite element modeling, we actually tell it whether or not we have plastic deformation. If we have plastic deformation, we have to go back and change how we're doing it. Everything we're doing right now is assuming that when we release the force, it's going to come back to its original state. We have no plastic deformation in this model. So, and this goes with the equations too. This isn't we're sitting there and we're working with equations on some complex shape. The equations actually allow for infinite stress. And that's what's happening in that corner. If we actually take the value of x and y and we plug in 0 for x and 0 for y, that's where we're at, right? In that case, when we plug those values into that equation, we're going to get it. So I can keep making my elements smaller and smaller and smaller and smaller, and at that point my stress is going up and up. It's never going to converge. That's why we don't have corners like this. We try to avoid corners. Or that we know in that little part of our model, the numbers aren't that correct. So we can do things, I just need to make the edge a little round and I fix my problem. It's a mathematical thing, okay? It's when I put 0 in there and 0 in there, I kind of get divide by 0 kind of thing, and I get infinite. That's what I'm saying, when we're putting smaller and smaller numbers in it, when I make my elements smaller and smaller, it's using smaller and smaller values. But it's still gonna get infinite at that. And it's averaging it over the stresses, averaging it over the element. That's why we don't see infinite, that's why we don't get infinity. So I already know this is a problem with finite elements. And a lot of times, let's say, if I have a square plate, and off the surface of this square plate, I have a cylinder coming up. Where the cylinder is in contact with the plate, what do I have there? 90 degrees. So at that point, anytime I have 90 degrees, I'm gonna get infinite. I know this is going to happen. So one, I can put a fillet there. Or two, I can minimize it. One of the ways we minimize it is we come in and I make my mesh fine right there, right? So I come in and I put a brace there. So at that intersection, why would somebody take off marker? Alright. So it's still not nice and smooth. If I come over here, return to my model, I'm gonna click here, I'm gonna go to my FEM. Here's where I did my map meshing. I'm gonna go ahead and edit this. If I look at, I use quad force, right? I use linear. That's not that great. There's no reason why you should be using linear in this class. You will lose points. So I'm gonna try to do a little better. I'm gonna click here. I'm gonna use 6-noted triangular elements. Preview. Boom. Okay. So I've got that. I'm gonna go to my CM. Over here. That's how easy it is. And now there's some other issues with this. Okay? I already know that. And you'll see them when we look. Displacement, no big deal. Stress element, no. Yeah, it's a little bit better. We still have this little stuff right here. We're not going to get away from that. And we have, look, I see this, right? That's not what I want to see, okay? But you already understand it's a problem because it's this corner, okay? If it was rounded, we wouldn't have this problem. And there's course methods going on over here. Alright, everybody good? Those did a lot. Any questions? I'm starting to do the homework and stuff, so some of you may have already noticed.